All right, so we are going to look at the uniform distribution. And so now in looking at the uniform distribution, we first need to consider the discrete version of it. If we don't, some of you may not really understand what we mean by a uniform distribution. So we will be looking at that in a short moment. So to start with, your uniform distribution is trying to say that for each possible point, you have the same probability. For each possible point, you have the same probability. That's what your uniform distribution is telling you. So if you have maybe discrete values from 1 to say n, the probability of each of these values, maybe you have 1, 2, 3, let's assume there are only 3 points, 1, 2, 3. The probability of each of them will be 1 over 3. All right, let's do it now. So the discrete uniform distribution. So the uniform distribution, as I said, what we are considering here for the discrete uniform distribution is that the probability of x, capital X, equal to x will be at any point in time 1 over n for all x equal to 0. Okay, we don't start from 0, we start from 1 because our concern is in this case 1, then we go to 2, then ... depends on how many values you have, then n. Now, an example is we can take it from your fair die, for instance. If you, okay, let's leave the fair die alone, but it looks something like that anyway. But assuming that we have P of x, that's the general case, P of x equal to, okay, let's do something first. Let's assume that we have a line like this, and the first value is this, and then it ends at 5. Now, if we divide this boundary into 5 equal parts, we are going to have something like, okay, perhaps 4 equal parts. 1, 2, 3, 4. Yeah. So let's have it this way. Supposing that, look at, please don't disturb us. We need to mute your mic. So 1 and then 5. Note something. The beginning was 1 and the end was 5, but we have divided this into 4 different parts. So the first part, the second, the third, and the fourth. So we are trying to bring out something uniform. When you have this kind of distribution, we say you have a discrete uniform distribution. So what happens? If I want to look for the probability of 1, I'm going to have it to be 1 over 5. And that's going to be the probability for all other values, probability of 2, probability of 3, and up to probability of x being 2, okay, being 5. So it's the same thing for all of them. And when you're done, you end up getting something like probability x equals to 5, okay, 1 over 5. Don't forget, we said that the probability that x is equal to any of the x's you have here will be 1 over n. So your n is this. So the n is the last digit that is showing there. Now, in this case, what is our distribution? Let's look at what we have done. This is simple. We are saying in this case, we are going to have something like probability that x equal to x equal to 1 over 5. X equal to 1, 2, 3, 4, and 5. So that is the case in this, in what we are looking at here. Right. So that is the case with what we are looking at here. And so in that case, the probability that x is equal to 1, as well as the probability that x is equal to 2, as well as the probability that x is equal to 3, and we continue like that until you get to x is equal to 5, is 1 over 5. It doesn't change. So that's a continuous uniform distribution. Now, but this one is discrete. So this is the PMF. But what about when we get to we get to a continuous version of it? How is it going to look? Well, before we go to the continuous version, there is a more general way of writing this. The uniform distribution, and that one is appropriate for any situation in which each of the possible outcome of the random variable has an equal probability of occurrence. And now, so it's a more general way. I'm going to write it on the board. So in that case, we'll be considering something like probability that x equal to x. So a more general formula now will be equal to 1 over b minus a plus, you're going to have a 1 plus 1, everything multiplied by x. Now, our concern, sorry, like that, no multiplied by x. X is going to be 1, 2, and then it continues until it gets to, sorry, not 1, 2. In this case, it's going to be a, comma, a plus 1, a plus 2, a plus 2, and then until you get to, so you continue a plus 3, then until you get to dot, 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 then b. All right, let's make it simpler. B here is going to be your 5 in this case. So the n, what you call your n, what we called our n the other time, which is this, is going to be our b. Okay, so what we call our a, that's going to be 1 in this case. So let me write that so that you get it. In the simple case, in the case above, where we had, I mean this diagram above, please. The diagram here, a is equal to 1, and b is equal to 5. So the highest value of your interval is what you are going to call that. Now, so in this case, we are going to have it that it will be equal to 1 minus 5. B is 5. A is, don't forget please, B is 5, and A is 1. So 5 minus 1 plus 1, and you already understand that that is going to give you 1 over 5 as we had before. So x will be equal to a. What is a? A is 1. So a plus, sorry, I wrote a plus 2. It should have been a plus 1 before a plus 2. So let me clean that. So this is a more general way of writing it. You notice that you have the same thing. So a is 1, that's from here. A is 1. Then when you take your 1 and you go on, you're going to have a plus 1. That's 1 plus 1. It will be 2. Then 1 plus, oh, sorry, this should be 2. Comma, a plus 2. So you have 3, and then you continue. If you continue, add 1 again, that should be a plus 3, that will be 4. Then a plus 4, that will be 5. So the formula you have here, as well as the first one I wrote, this one, are 2 ways of specifying your continuous discrete continuous distribution. For me, I prefer the first one because it's easier and easier to remember and easier to use. The second one is a more general way of writing it. So if you prefer to use it, you are also fine. You will not miss it. Okay, let's do it for the formula alone. So whichever one you are using of the two, you are fine. All right. So that gives you the discrete continuous distribution. And if you are interested in seeing the cumulative density function for it, it's the cumulative density function of the discrete uniform distribution will look something like probability. All right, let's continue. That x is less than x, right? Or less than or equal to x, equal to. Now it will be equal to, if you remember, I told you call this capital F of x. All right. And that will be x minus a. So that particular, any particular x you're using here. So let me put this in small letter. X minus a. Don't forget that this is always capital letter and this is always small letter. X minus a over, okay, plus 1 over x, or rather b minus a plus 1. So please, that will be the, that will be the cumulative density function when you are looking at the discrete uniform distribution. So the discrete uniform distribution consists of an interval divided equally into portions equally. And at the end of the day, you know, this one from 1 to 5 now, it's divided in such a way that we have 4 different intervals, 1, 2, 3, and 4. But for each of the values that we have here, we have a probability, so that it is 1, you have it to be 1 over 5, probability that x is 2, 1 over 5, probability that x is 3, 1 over 5, probability that x is 4 is 1 over 5, and like that, and probability that x is 5 is also 1 over 5. Now you get something from that. We can now go into what we call the continuous uniform distribution. Now, I don't know, perhaps you may have a question or something. Okay. All right. I don't know if anybody has a question before I go into the continuous uniform distribution. Any question, please?
No, sir.
Okay. You don't have a question. Okay. So you just know that each possible value in the sample space has they have the same probability of showing up. So that's the case with your fair die. If you remember, we used to say probability that x is equal to any of the values. So in this case, I'm going to use I. Okay, is equal to 1 over 6. That's for your fair die, where I is equal to 1, 2, 3, 4, 5, 6. So for 1 to 6, the probability is 1 over 6. Is that true? Is that true?
Yes, sir.
All right. So this is a uniform distribution, a discrete uniform distribution, actually. And that of tossing a fair coin once also follows this distribution. Hello? So your fair coin, probability x for fair coin now, x equal to whether you say head, so or tail.
How many students are students?
So usually we want to use 0 and 1. So let me just use I. and use 0 and 1 equal to 1 over 2. I equals to 0. Please mute your mic. If you are discussing, you should not be discussing in the class. Hello? If you have to settle something, please mute your mic. And 0 has to do with, maybe it could be tail, and 1 may have to do with head. So this is also a continuous distribution. In general, if you have you have values from 1 to n, and the probability of selecting each one is the same, then you have a uniform distribution. So maybe values from, it may not be from 1 to n, it may be from maybe 2 to 9, it may be from 3 to, but usually, let's call it 1 to, it's usually 1 to n. So if you have, generally, you have values from 1 to n, and then you need to pick, you have equal probability of picking any of the values, then you have a discrete uniform distribution. So as long as you're talking about individual values, discrete values, 1, 2, 3, 4, 5 to n. All right, so that is the case. Okay, and you may also have it from maybe 3 to maybe 7. You may have it from, but the main thing is that regardless of the way you have it, each value has equal probability of being picked. Hello, do you get that, please?
Yes, sir.
Okay, so let's go back. So the difference between the first formula we wrote and the second formula is that the first formula only allows you to start from 1.
Yes, sir.
Okay, but the second formula allows you to start from any number. So you may not start from 1. It may be from 3. Okay, let's say it may even be from 6 to 12. And so if you are doing that, it means that you will have to start saying, okay, in this case, my probability will be 6 minus 12, and that is going to give you 1 over 6 for each of them. And then your range will be, I'm doing this, please. Okay, let's not do 6 over, that will be, I think we need another page, sorry. So we'll not make it confusing. I want to leave this, but I feel it will be justice enough for us to apply this once and see situations where you don't have it to be 1 over n. Okay, now, so dealing with the second formula, if my range of values are such that my B is maybe from 3, okay, let me use what I was using before, 6 to 12. Now, what happens is that the probability that X is equal to whatever it may be, any one of them you already know. So even if I put 6 here, it will still be the same probability for each of them. So let's just put it as X for now. Probability that X is equal to X now will become 1 minus, don't forget, in this case, our A is 6 and our B is 12. So that becomes 12 minus 6 plus 1. So, and that will become and that will become 1 over 7. I believe I'm correct. So, and that means our range, so maybe I should put it down here to save our space and or make it neater. That will mean that, so A was 6. So the first value we are going to have for our X will have to be something like 7. Okay, no, 6. A was 6. Then we'll have 7. A plus 1 is 7. A plus 2 is 8. So you continue 9 until you get to B, that is 12. So you continue 10, you have 11, you have finally 12. All right, so that is how to apply it in a case where you do not start from 1. So the difference between the formula you see here, this formula, and the other one is that in the first, you are starting from 1. Necessarily, it has to be from 1. But the general formula, because you may not start from 1, is this. Whether you start from 1 or you start from any other number, you are going to be up. It's going to be appropriate if you use this one at any point in time. So that's the difference between the two. All right, so we go to the continuous uniform distribution. A continuous random variable is similar to, the discrete version of it, except for the fact that A and B may not be, necessarily integers. So that means that the values between A and B are real numbers. A and B themselves may be real numbers. They may not necessarily be whole numbers. But then between them, when you create a sub-interval, you try to put a division. I'll go back again. So we're looking at, you understand now, I believe. Continuous uniform distribution. So this time around, this is what we are doing. The same thing applies. We have an interval, a straight line, for instance. Now, perhaps I should use a straight line here. All right. Now we have this to be maybe 1 and 5. The other time we said A equals to 1 and B equals to 5. However, we may not have this to be an integer necessary. Could be 1.2, could be 5.5. All right. But even if it's an integer, we are saying that this time around, the divisions we are going to be having could be in such a way that we have some decimal points. So the difference between what we are looking at here and what we looked at the other time is that we now have decimal points involved. So, and that is what we made as a distinction between the discrete random variable, if you remember, and the continuous random variable. The fact that you are considering infinite number of points, every possible number in the real line between the two limits that you have here. That means between the interval of 1.2 and 5.2. So in that case, the discrete continuous uniform, the discrete uniform distribution will not be appropriate. So we need to use the continuous uniform distribution. Now, what do we do here? Looking at this, we will need a different PDF. It's similar, but somewhat different. So what are we going to call our PDF? We had a PMF the other time, but this time around a PDF. The probability density function will be 1 over B minus A. Note that B must be greater than A. So you may not see this written, but I'm writing this just to, all right, let me leave that first. We'll come back to it. X will take value between A and B. So you are going to have it this way. And note, I'm adding this to the equation. Where you may not see this, but if you check the textbook or something, depends on who defines it. It should be noted that in this case, B should be greater than A. Okay, so I believe it's already shown here already. So if S is between A and B, so definitely B should be greater than A. All right, this is the case. And we have A to be our minimum and B to be our maximum value. And there are certain things that you need to notice. Everything that applied in the first one applies here, except for the fact that we now want to do this with values that are not discrete, they are continuous. So let's look at some applications of, okay. I want us to look at some applications of the continuous, or rather of the uniform distribution. Now, the first one is your p-value. There's something called a p-value. How many of you have heard of p-value before? How many of you have heard of something called p-value before? Nobody? Okay. So you people are not answering. How many of you have heard of a p-value before?
I haven't heard of something like that, sir.
All right.
Heard of it, sir.
You have not. Okay. I think you maybe because you're just coming up anyway. But when you start, for some of you, analysis, when you start some things on data analysis, you get to know more about that. But let me quickly now in statistics. So we're looking at application of p-value. Application of the uniform distribution. Application of the uniform distribution. So okay. Now, in statistics, when the p-value is used as a test statistic for a simple null hypothesis, the distribution of the test statistic is continuous, then the probability, the p-value is uniformly distributed between 0 and 1. Now, you may not understand this particular one, but I cannot explain, or rather, it's not within the, it is not within what the course we're doing now does not actually say I should teach you p-value, but you can understand this one, and I will do that. P-value is a probability value. You can find it for a particular test statistic. And that test statistic is something you do in order to decide, you find in order to decide whether you're going to reject a claim. Somebody may say the average age of students in your class, for instance, is maybe 19. And then I say, okay, that means the person is saying that mu, so we may say H naught, null hypothesis. That's what we call H naught. Don't worry if you don't understand everything. Just understand that somebody is making a claim. Mu equals to 19. That means the average age of students in your class is 19. And then H1, somebody else, maybe somebody is trying to prove or disprove this claim and say, okay, no, it can't be. He may say mu is not equal to 19. And so when he says that, we'll get data, we'll do some calculations, and then we'll obtain a test statistic. A test statistic, that's what you're seeing here. Oh, not this now. A test statistic. So, and then when we obtain that test statistic, we can obtain a p-value for it. P-values are probability values. Each value that the test statistic can take has a probability value, which we call p-value, that can be used to check whether or not we are going to reject the claim, this claim. Do you understand that, please?
Yes, sir.
Okay, so the p-value is a probability value, so it takes value between 0 and 1. So in that case, you already know that this is a continuous distribution because its values will be between 0 and 1. So the maximum and minimum is this, that would be our A, and the maximum is 1, that would be our B. All right, so that's one of the applications. For some of you who will be going into data analysis, Hello, sorry. So as I was saying, the p-value is just one of the applications. I believe you can hear me. Hello,
Sir.
you can hear me.
Yes, sir.
All right. So the p-value is just one of the applications of your continuous distribution. So I was saying that the reason why it's that way is because you have a minimum and you have a maximum, the minimum 0, maximum 1. And each possible value of the test statistic, you know already that we will not be having, so it's uniform, but it is continuous, if you look at it very well. All right, then we go on to, well, I'm trying to get my board back. Okay, we don't have time, so maybe we should just continue like that. So that's the first application. The second application is when you run simulation experiments, many programs can actually generate that. And you can use you can generate random numbers using the standard uniform distribution. Don't worry, you get used to that when you start writing your own programs. And then the uniform distribution is useful for sampling arbitrary distributions. So that's another use of it. A general method is the inverse transformation method, which uses the cumulative distribution function. You can read that from your courseware. So it's useful for sampling random distributions. So some of these things may not be easy to explain to you at the moment because you're just coming up. And so all right. So we are looking at the mean and variance for the uniform distribution. So in the case where we have permit me to use the word DID to mean discrete uniform, I mean DUD to mean discrete uniform distribution, and to use CUD to mean continuous uniform distribution. So that way we can put a gap between them. So need to notice this now that first of all, the mean for your discrete uniform distribution will be A plus B divided by 2, and that will be the mean for your continuous random, continuous uniform distribution also. So where they differ now is in terms of mean and variance is in terms of the variance. Now, don't forget that this is not the only difference between the continuous and discrete uniform distribution, but that we also have something we discussed earlier, the fact that in the discrete, you can have only integer values, but in the continuous, you can have decimal values. Don't forget that. And you take the others that have to do with them as with all other continuous distributions. Now, so looking at the variance for this particular one, its variance will be something like B. I think I may need to clean this a little bit. So V of X will be equal to B minus A plus, okay, so we have plus 1 all squared. Okay, so it will be squared, and then you have to remove 1, and then you divide by 12. Now, this will be the variance in the case of your discrete uniform distribution. But in the case of your continuous discrete distribution, it is going to be somewhat different. And what do I mean? It will look something like variance of x equal to, now you're going to have b, the same b minus a, everything in brackets squared over 12. So that's the difference between the two. You'll notice that in the first one, that is the discrete version, we have b minus a, then plus 1, and everything is squared, then we subtract 1 before we divide by 12. But in the continuous, it is just b minus a raised to the power of 2, all divided by 12. All right, so these are but a few differences between the two. There are other properties, but for now, we are considering the mean and the variance. I've talked about that. If you check the CDF cannot be the same. The CDF,
Sorry, sir.
okay.
In variance, you said b minus a plus 1 divided by 12 all squared, right?
B minus a plus 1, yes, yes. What's any issue? You can
No,
see
sir, I
it,
just want to confirm.
you can see it from the screen, right?
We didn't see your board, sir.
You can't see the board? Even now?
Yes, sir.
You can't see the board now?
Yes, sir. We are just seeing your image, sir.
Wow. Okay. All right. Sorry about that. I don't know what's really happening, but
Well, sir, I can see the board.
okay. Who again can see the board?
Hi, sir. I can see board.
Okay, young man. I suggest maybe you try to look at the stuff well, so that if you have any issue, you may be able to check and find out what is happening. Please. I'm sharing the board is actually what I'm sharing now, so I don't know. All right. I believe you'll be able to resolve that. So now we are done with that. Let's look at the CDF. Now, if you remember, we talked about the CDF for the discrete distribution to be, okay, we need to talk about that. Probability, the probability, let's see, probability that X, capital X, is less than X. So let's use that now. Less than or equal to X to be equal to A. Okay, so it should be B minus A, or rather X minus A divided by B minus A. Now you're going to have a plus 1 in both cases. So you have a plus 1 here and another plus 1 here. All right, so this is A, please. So you have an A here. Okay, so this is the first case. And then we are going to also have a probability X is less than X here. This one, in this case, is going to be the one we had the other time. We will not have it. So we just have X minus A. And then B divided by B minus A. So there are other properties, as I said before, apart from these ones, there are other properties, but these are the ones that are more important to us at the moment. So we only consider these ones. Now, I want you to know that we will be doing some examples on this. And so let's continue. Now, going on, we look at, supposing we are giving a question that looks like this. You already know that when we say P of X, Okay, number one, let the question be. Given f of x, okay, p of x equal to 1/8. We may use 1/8, but it doesn't have to be 8. Let's use something else. Let's say 1/10. X equal to 1, 2, and to 10. In this case, I've made it short because I want to save space. But if you have something less than, less than 6 thereabout, you may, in fact, even 10 is not too much to write. So maybe I should just take the time to write all of them. 4, 5, 6, 7, just to give you a good culture. 7, 8, 9, and then finally 10. Now, if we have this is one example. So let's call this one given. Find the variance. Okay, we may find a number of things, but let's see. Find the mean and the variance. Find also the probability that x is at most 7. So let's use the word 7 here. Now, this is one case. I will want to put another case that looks similar, but not exactly. And this one will be a continuous case. So we're going to deal with that too when we finish the first one. Now, given f of x, and don't forget, I told you 2 things that you can use to identify whether you have a discrete distribution or a continuous distribution. The first one, and which does not usually fail, is the fact that when you have x in an interval, what you need to check if they don't specify that, okay, we say 1 is less than x is less than 10. So you don't need too much things to know that this is a uniform distribution. The moment you're able to see that you have 10 here, 1 on top, and then you have 1 to 10 again here. So you already know that this is a uniform distribution. And in some other cases, it may not look something like this. Perhaps it looks something like maybe 6. Okay, let's leave that for now. You can always decipher if you are not told that it's a uniform distribution once it looks something like this or this here. And you know that this one is continuous, partly because you have f of x. Yes, I can use f of x for the discrete version, but I can also use p of x, so it can be interchanged. But conventionally, we use f of x for the continuous version. And then, but the primary thing that tells you that this is continuous is the fact that x is an interval. X is in an interval. Okay, x takes values in an interval. All right, so, but we are also told to find the mean. We can't say find the probability that x is at most 7 here because we consider intervals. This, if you know what we've been talking about, if I ask you to find this, a particular point value for a discrete distribution, then it will be 0. It is only for an interval that you can find, you can look for probabilities, you can actually find probabilities, but for a point value, the way you do in this one, it won't work out the way you do in the discrete. So if you come here to, if you come to the discrete, you can find at most 7. You can, at most 7 can work here. But if you are looking for the probability that x is 7, you get that here to be 1/10. 1/10. But here, it will be 0 because you cannot get it for a point value. All right, so we may still find the probability that X is at mod 7, but let me add one more thing. Find the probability that, okay, find probability that X, okay, let's say 0, no, not 0, 2 is less than X is less than 5. So we may find this probability also, and in that case, we may proceed. Now, the first example, I would like to cut this one off and take it to another point, another slide or page. All right, so make it neater. So the first example in dealing with this now, we will have to actually have E of X, from what we discussed before, E of X should be A plus B over 2. So A plus B over 2, that will be the mean of this distribution, and that will be 1. Okay, so let's define our A and B. Our A will be 1, and B will be 2. Therefore, our expected value of X will be 1 plus, sorry, B will be 10, not 2. B will be 10, since that's the range we have here, this place. And since that is what you have here, in this case, so plus 10. But I want you not to forget that I'm using a simpler version of what we can actually have in practice. And I've given you 2 exercises. There are times where you don't have your range starting from 1. Your range may not start from 1. But the moment you are able to identify it as a, that will give us 11 over 2. So the moment you are able to find out that you have a discrete random variable, but it doesn't start from 1 in terms of the range of X, then you need to resort to a different kind of mechanism. The mean will be the same, but the probability, I mean, how you define your stuff will need to change a little bit. So even if we started from 2 here, and we started from, maybe we went from 2 to 4, in this case, you should be able to tell that this is your A, this is your B. And so that means the probability will be 1 over 2. Okay, so your mean would have been 2 plus 4 divided by 2 also. So don't forget that. And we can find the variance. What will be the variance in this case? The variance is going to be something like we said B minus A plus 1 all squared minus 1 all divided by 12. And so we are going to have that to become we said our B is 10, A is 1, 10 minus 1 plus 1 squared minus 1 all over 12. And that should give us what we need. So we will have it to be 10 squared, that's 100. Minus 1 over 12. And that is going to give us 10,000 minus 1 over 12. That is going to give us 9,999 over 12. So what should that be? Anybody who wants to give us the answer?
Sir, it's not 1,000.
If there's
It's
a
100.
mistake, if there's a mistake, you can point it out, no problem. Oh, sorry, I'd made it hyped. Sorry, I get that. Thank you. Here It's still going to be 10. Sorry,
Yes, that will be 100.
sorry, please. It becomes 100 minus 1. And that becomes 99 over 12.
It's 0.25.
99 divided by 12, 8.25.
8.25.
Yeah, thank you very much. So 8.25. All right. Now, so now if I ask you to find the standard deviation, the simple thing, standard deviation of x, that was not in the question, but in case you are asked to look for that, it will be the square root of the variance of x. And that will become, so square root of 8.25, that should be 2.87, 3. Okay, so that's it. Now we're done with that. If you were asked to find E, all right. Sorry, the network went off. Can you hear me, please?
Yes, sir.
All right. Let me get my whiteboard again. Sorry. I may not be able. Okay. That's all right. The whiteboard is coming up. So the variance of, the standard deviation is 8.2, is the square root of 8.25. And that should give you
2.87.
2.27, sir.
2.87.
8722. 22.
All right. So if you are asked to find the expected value of x squared, it will be variance of x plus the expected value, the square of the expected value of x. And somebody may say, how is that? Yes, that is true because we got that from the variance of x, which we have defined earlier to be the expected value of x all squared minus the expected value of x. Okay, sorry, the expected value of x squared minus the, so by changing the subject of formula, you are going to arrive at this one. So that is how we got that. And in that case, you just need to sum up what you have from your variance. The variance was 8.25. And then your expected value of x was found to be 5.5. And if you sum the two together, you should have 13.75. I guess I'm correct. Right? All right. So that's that about that. Now we can go to the continuous version of the question and see what happens there. Now, in this case, the mean is the same thing as what we had before. So I'll just find a way of copying that and taking that there. The mean will be the same. And so if we have a continuous variable here, we'll have the same mean. But there are some other things that are not the same. Okay. There is something we need to check first. That we didn't finish. There's a last part of the question that we said find the probability that S is at most 7. You don't need to do this if they are not specified. The two here I have here, these two, you don't need to from the standard deviation to this. I just did that to show you in case you are asked to look for that. But we were told to find probability that X is at most 7, and that will be probability that X is less than or equal to 7. And in that case, we can go by saying the first thing is we may use the formula we had learned earlier, which was x minus a plus 1 over b minus a plus 1, and we get what we are looking for. So x minus a plus 1 plus b minus a plus 1. Is that true? So in this case, we could go by saying this, and then we just have, what is x in this case? X is 7. So let's put a general formula for that first. We'll have x here. And then now we'll come up to say, okay, probability that x is less than or equal to 7 will now be 7 I think I can record. All right, so we are looking at this, and then we have to put our 7. We'll have 7. We know A to be what? What's our A again, please? If you can remember. What's our A? And what's our B? Nobody?
Our A is and B is 10.
Our A is 1 and our B is 10, sir.
Yeah, that's correct. So A is 1 and B is 10. That's correct. So we're going to have 7 minus 1 and 10 minus 1 plus 1. So at the end of the day, we're going to have 6 over, wait, I'm supposed to put 1 here, plus 1. And so at the end of the day, we should have, this should not be 6 anymore. This should be 7. We should have 7 over 10. Now, this is just the way to do it with the formula. If you prefer to do it that way, you could actually say, okay, I want it this way. Each of them is 1 over 7. So if you are doing probability that x is less than or equal to 7, then you could just say, all right, that will give me the sum of 1 over 10 7 times. Do you get that, please? Do you get that, please?
Yes, sir.
Okay, so otherwise you may go by this formula. So probability that x is less than 6, for instance, will mean summing 1 over, multiplying 1 over 10 by 6. All right, but it's preferable to use this formula, I believe, because so that you don't get it wrong anyway. Because sometimes you may just have 1 over, it may be 1 over 10, for instance. Okay, so we're going to have 7 over 10 as our probability. So don't forget we have a less than or equal to sign here. So that's it. Now we go back to the continuous type. Now the variance, if you remember, is somewhat different, and the variance is actually B minus A, even if you say A minus B, it's the same thing anyway. B equals to B minus A because you're squaring, so it doesn't matter if you put A first or B first, really. But what matters is that, so raised to the power of 2 divided by 12. And that will be, in this case, because we have, the questions are similar. This is what we have. A is 1, B is 10. So we are going to have 10 minus 1 all squared divided by 12. And you will notice that we seem to have the same variance. Is that true? 9 squared, but not really the same. Well, perhaps we may say close, but not even very close. The other one was 99 over 12. It's not the same. So we are going to be having 81 divided by 12 as our variance. That should be 6.75. All right, so the other things that need to be found, the things like the variance of x and the others. I mean, expected value of x, I believe you can find the expected value of x squared, but I want to quickly go to looking for the probability that x is less than, all right, no. We had probability that x is at most 7. So less than, you can also find probability that x is at least or greater than or whichever one you're looking for. So x is at most 7. That can be found, and that will actually be equal to. Now go back to your the formula given before now about your random variable. You notice that we said probability that x is less than or equal to x is x minus a. Okay, let's do for x first, then we'll do for 7. Where's the clean again? All right, let's do for x first. So when we do this for x, we're going to have x minus a, very close to the one we did before, then b minus a. That's going to give us, that's what we are going to have. And if we have that, we are going to have it to be, we'll have it to be that the probability of x less than or equal to 7 will be equal to 7 minus a is our a is 1, and then b is 10. So we have 10 minus 1, and that is going to give us, what would that be, please? 6/9, right?
Yeah, 2/3.
So that becomes 2/3. So
0.6.
if you like, you may come and say 0.667, 0.6. I want to write a 0.6667. All right. Now the probability, one more, the last one, we are able to finish this one. We are done for this. That 2 is less than x is less than 5 will now be it will be just doing it for 6 and doing it for 1. You know the probability density function for 6 and that the one for 1 also. So let's do what I mean here. This is what we are going to have. This would be f of 5 minus f of 6 of 2 rather, of 2 so, and that is going to be f of 5 is 1/10. Is it 1/10? Sorry, f of 5 means probability that x is less than or equal to 5, and that's going to give us 5/10. All right, I believe you get that now. I believe you get that.
Yes, sir.
Probability that x is less than or equal to 5. That's what f of 5 will become. This, if you're sliding on the board, you may need to wait. All right, minus this one now is going to become probability that x is less than or equal to 2. All right, so in that case, sorry. In that case, we are going to have something that is okay. So there's an issue somewhere. I think we need to resolve that, but I'm trying to see how that can work out. Okay. In this case, it's a bit different, so we don't have any issue with that, and we can continue. Now, this is going to be from what we did up there. I don't want to write the formula again. You already know. We remove 1 from whatever it should be, and 1 from x itself and 1 from 10. So if you remove 1 from 5, what is that going to be?
4.
4. And remove 1 from 10, what is that going to be? 9.
Over 9.
9.
All right. So the next one, remove 1 from 2, what's that going to be? 1.
1.
1 from
9.
10, that will be 9. So that's what you have done here. The formula you used here is what you are using for that one also. So please, that's because A is 1. So you are removing A from X and A from B. B is 10. All right. That will now give us 3 over 9, which is the same thing as 1 over 3. Okay, so the final answer will be 1 over 3. And that brings us to, I think, the final thing that we need to know about the uniform distribution. So that will be all for the uniform distribution for this tutorial. Now we may go on to the normal distribution. The normal distribution is not difficult, but before that, I will not lose this recording. I don't know when the system may go off. All right.